So we'll just move on to Barbara's presentation, 3D hydrological modeling of the Fox Creek area, south, or Alberta, Canada. Go
Okay.
ahead, Barbara, it looks good.
So can you see my screen?
Yep.
Yes, I think so. Okay, so I changed a little bit the title of my presentation. So it is 3D groundwater hydrogeological model of the Fox Creek, Alberta, of the Fox Creek area, Alberta, Canada. So the principal objective of my doctoral thesis is to understand the eco-hydrological dynamic of the Fox Creek area located in West Central Alberta in order to evaluate potential effect of oil and gas development and climate change on the shallow aquifers. As specific objectives, I have to develop a 3D numerical flow model to better understand the aquifer hydrodynamics, which is the focus of this presentation. Then I have to develop a coupled surface water groundwater model that represents the interactions between both water components. Then I will couple this hydrological model with a land surface component to create an eco-hydrological model that reproduces the interaction between vegetation, climate variables, and linkage between the surface and subsurface processes, as well as the freezing thawing condition that they are usually neglected, and simulate future climate scenarios to investigate their impact on water resources. So the 700 square kilometer study area is located in the province of Alberta, approximately 4 kilometers west of the town of Fox Creek and 220 kilometers northwest of Edmonton City. And the topographic elevation varies from a height of about 1,180 meters above sea level at the western margin to a low about 780 meters above sea level at the outlet of the watershed. And the reason why we are studying this zone is because the Fox Creek area has been one of the most active regions of oil and gas development in Canada for the last 50 years. And at the same time, the most important groundwater supply comes from the Bascapa Formation here in yellow, which is the uppermost bedrock. So the study area is framed within the Western Canadian Sedimentary Basin, which is composed of sandstone, siltstone, shale, and coal here, corresponding to the Wapiti Formation. Then we have a very thin layer of about 10 meters of mudstone that correspond to the Battle Formation. And then we have the Scholar Formation composed of sandstone and siltstone interbedded with mudstone. And in yellow, we have the Bascapa Formation, which is a complex succession of interbedded mudstone with sandstone channels. All of this geological formation represents the bedrock, and at the surface, we have unconsolidated sediments that are divided in 5 subunits, and they are composed of sand, gravel, silt, and clay. With respect to the hydrogeology, the Bascapa Formation constitutes the main aquifer of the system, whereas the Battle Formation is an aquitar. For the groundwater model, we selected the free flow code, and a mesh of 45,000 triangular elements was created with 25 layers of different thickness in order to represent the different geological formations. And as boundary condition, a fixed head was imposed along the western part of the watershed and also along the 3 principal rivers. The Little Smoky River is the major one and it flows north, whereas the Smoke River and Tony Creek are both tributary rivers of the watershed. On the other hand, an no-flux boundary condition was imposed along the edge of the watershed. A recharge equal to 70 millimeters per year was assigned according to bibliography. And as hydraulic properties for the superficial sediments, we have qualitative values. So for the different subunits, so according to that, we assigned quantitative values that are between 1 to -6 to 1 to -3 meters per second. And we're just with respect to the bedrock, the model was calibrated considering hydraulic conductivity values from literature, and they come from different hydraulic tests, such as pumping tests, permeameter tests, and others. And for the Eber-Pascal formation, the first 100 meters, I consider 5 different hydrogeological zones. Whereas for the rest of the geological formation, I consider them as homogeneous, so just one value of hydraulic conductivities. It is important to mention that this donation for the Eber-Pascal formation was validated and thus justified against hydraulic conductivity values obtained from field data and also from bibliography, where the highest values are found at the northeastern part of the watershed, here in the bigger dots, whereas the lowest values in a smaller dots are located along the south portion of the watershed. This map shows the isocontours of hydraulic head, and they tend to follow the topography. So we have the highest values of water table elevation along the western part, with the highest value equal to 1,160 meters above sea level. And then it decreases until the outlet of the watershed with a value equal to 782 meters above sea level. Therefore, the groundwater flows from the south to the north until reach the rivers and the outlet. The model calibration included 161 observation wells distributed throughout the study area. This map shows the difference between the observed and simulated hydraulic head. So the underestimated values are represented by light colors, whereas the overestimated values are represented in dark colors. So according to this, we got a root mean square error equal to 6.6%, which is less than 10%. So the model results are considered as reasonable. And the study area is located in a seasonally frozen ground according to the soil temperature fluctuations throughout the year. So as I mentioned in my objectives, we want to represent these processes. So as future work, I will develop a cobalt surface groundwater model with Kathy, probably with this smaller study area of 420 square kilometers, in order to quantify the water fluxes and storage dynamic within the unsaturated zone, considering the soil under normal condition. It means no freezing processes. Then I will develop a couple groundwater surface water land surface model with Kathy, Noah, and P in order to assess the impact of seasonally frozen ground on the hydrological cycle, as well as on mass and energy fluxes. And finally, once the model is calibrated, we will run future climate scenarios. So that I will.
Great, thanks, Barbara. Excellent presentation. I'll open the floor. We have time for a few questions.
Always questions. That was great. If you go to a small area, is the actual hydrogeology going to be well enough known because the smaller you go, the more heterogeneity within your aquifer system becomes a problem. And at the scale you're going, the heterogeneity will average out and you get great root mean square error. But the smaller you go, the more problems that heterogeneities and sandstone channels within muds are going to become more prevalent and important to knowledge. And are you going to have that kind of geological knowledge to base a smaller zone for your Kathy model?
Yes, actually, well, we started with the aquifer, with the upper Pascal formation as an homogeneous, just to see where are the under and overestimated values. I know that this is a very big basin, 700 square kilometers. So is very like impressive in quotes for me that with just 5 hydrogeological zones, we got a very good root mean square error, because it is expected that, as you say, a bigger watershed will be more heterogeneous. So, but these results were also validated. So with 5 hydrogeological zones, it can be a good result if we are.
Yeah, that's right. The larger the area, the more those heterogeneities become. Each individual heterogeneity becomes less important, and the average becomes more reasonable. It's more when you get down to small. When you're getting into the unsaturated zone and the soils and recharge, you're getting into a much smaller area that with a much higher resolution needed for your aquifer characterization, and that I'm just wondering, do you have that kind of higher resolution geological data?
Okay, yes. For Cathy model, yes, this is a much more complex code. So for that, I will not only consider the superficial sediments, but also for example, the different kind of soils. But we will work with a very high resolution raster dam of 25 meters. So we will have a lot of computational effort. We know that, and yes, it is like this, and yeah. But
It's going to be fantastic when it comes out. I mean, I think that's a really important try it at least, and get. Cathy is complex, and I've tried it and never succeeded, but it is complex, and it's worth trying for sure.
Yes, but probably we will not consider, for example, from the scalar formation to the wapiti formation, because in some sensitivity analysis where I take those formation off, we realize that the aquifer system is mainly driven only by the past couple formation. So
yeah, that's what I would expect. Yeah, especially when you're wanting groundwater surface water interactions. The lower ones are going to be important in very localized spots, but for the most part, it's going to be the uppermost 10, 15 meters.
Yeah.